So the improvement in computer science comes from speeding up an algorithm, regardless of what machine it's running on, even if it's running on a Turing machine, right? Remember, so if you have a program on a Turing machine, it could take like a few million years to complete, right? A simple program. Even take a simple program that needs to sort a list, right? Sort a list in ascending order. If you give it to a Turing machine, it's possible that the machine could take 5 million years to complete that. Theoretically, it will. The important thing is that it is going to complete, right? It will do it. And but that's not the reason to switch from a Turing machine to something else. You got to get the algorithm fast on a Turing machine, and then do it on a different machine. Hey, this is fantastic. Is this an iPad?
It's PC.
Oh wow! How did you get your calculator on the side and then
it's a virtual calculator?
Comment on it. That's really cool.
Okay. Hi guys, this is Ben, and I'm very basic, very new to the programming thing, but I read the part to how to convert a decimal to hex, so I will try to show the process, and I'll go at my own pace. So, and feel free to help me out if I go into issues. So this goes to hex. And it's the exponent. Is it called the exponent? Is 16.
Base. So, yeah, I call it the base.
The base.
Because the base is below and the exponent is on top.
Yeah, it's a logarithmic function.
So what we need to do is to divide this number by 16. So we will have the first digit. So this number divided by 16. So I will put it here. 1, 2, 2. Can you see it? It's blocking.
I can't see it.
That's better. 1, 2, 2, 4, 6, 2, 9, 1 divided by 16. We'll have this number, and then we have 0.1875 left over. And then when we time this this number after the decimal to 16, then we'll get the remaining digit. So we get.
Is there a modulus operator on your calculator?
I do not know what that means.
Modulus means it's a remainder after taking the division. It'll say percent. I can't say percent, but is there a mod operator on this TI calculator? Does anyone know?
I downloaded it a couple of days ago.
Let's see. I don't see one. Just looking at his numbers, like his.
I'm surprised because modulus is a very common operation.
Unless it's
remainder. Is there something called REM? REM. Is there a key that has the label REM, remainder?
So
I do not see that.
Okay.
Something to note, Ben, what you could do is the 0.1875 isn't actually the real remainder that you want.
Yeah.
So Anne is actually talking about mod, which you could find by just entering, which this calculator I don't think will give you, but modulus will give you the real remainder that you want. So you could just quickly type in 1246291 and then the percent sign and 16 into Google, and I'll give you the modulus remainder that you want. And then from then on, just divide and then so forth.
Fantastic. Thank you so much, Susanna. That was a fantastic suggestion.
I still not get what's
can you do that? Can you do what Susanna suggested? Just copy that number.
Just copy the number.
Yeah. Alrighty, I did. And what should I type in Google?
Just a percent sign and then 16. The percent sign in for programming is the modulus sign, which gives you the leftover.
The remaining 3.
The remainder.
Let me share screen.
Yep.
Need the Zoom thing. Okay, let me see. I can share screen on that. Oh, that's perfect. That makes my life much, much easier.
Fantastic. Thank you so much, Susanna.
Okay, share screen. Is that the right one? Well, I guess I can just continue with the
previous. Go ahead.
I'm just gonna continue with the previous one.
Mm-hmm.
this is my old way, and then I put this number times 16, it gave me 3. And then what Susanna mentioned was that put in Google this number, do percentage 16, and then it directly gives you a 3. And then the next number would be
765, 393.
yes, 765, 393. Also do the modulus. Is it called modulus?
Good,
Let's do
percent,
the
percent.
remainder is what it's called.
The remainder, and then 16.
Also, I do like how your old method did work.
Yeah, I was planning on the old one, but I'll try this one too. Yeah, this is a bit new to me. 3 divided 16, and then the remainder is the remainder is
Hey, someone else can calculate the remainder and tell him to
Yeah.
verbally, right?
1. At least that's what I got.
but then Google doesn't tell me what's the number coming after that, like
Oh, you
dividing by
can go ahead. Yeah, someone else was trying to tell you.
repeat until you can.
Oh, so all right. So Ben, to get the number you want, instead of the percent, you would say slash. That's a divide sign, right? So the URL bar in most browsers, in Chrome and so on, it's actually a mini calculator. It's a calculator. You can actually type an arithmetic expression there, and it'll tell you the answer right there.
Really?
Yeah.
Or hey Ben, do you know Python? If you know Python, you can open up like a Python shell.
I am
idle shell.
Yeah,
No,
it's really easy.
Programming.
Hey,
Yeah.
Robert, no, I think this will be easier, right? Because Python, you got to get into the shell, whereas here, you type in, URL bar.
I see.
Search bar. You just go to the URL bar, where you type the URL, you can just type it in there in Chrome, and it'll give you the answer without leaving the page.
Susanna, what should I do? Because I put the original number, and then I put a percentage 16, and then it gives me 3 as a remainder. Then what would be my next step if I don't know what's the, this number divided by 16? Do I just do it here?
No,
you have to do it again.
No, don't do it. Just turn the percent into a slash and hit enter.
Yeah, turn the percent
right.
into a slash. So do that first.
It's doing the exact same thing that you were doing before.
Okay.
Yeah.
And then that. So then you get, that's your number.
Then you're gonna have to do
That's my
the same
number.
process you did before, where you just divide it by 16, and then your remainder of 16. So
Okay,
that's your
perfect.
remainder, and then you find the divide, whatever that was, just divided by.
Just keep on doing that.
Okay. So our last digit was 3. The first digit was 3, and then the second last was 1. And then we get this number divided by 16 again. So we get this number.
Yep. And then just keep on dividing it.
Oh, so we get all these divided number first and then do it?
Yeah, you could just do that. I think I'm getting confused with the other.
Yeah, no, that looks right. Yeah, I think that's exactly, do what Susanna said, and you'll get the answer.
I was gonna go with my basic
think
way. Okay.
Either way.
When you're doing your own, personal calculations, I honestly think your method makes more sense to you, and you should use your method. But
What
guess
works?
for-
What works?
Yeah,
if it works
I'm
for you,
sorry.
yeah. If it works for
I
you,
agree
it works
there.
for you.
I agree. Because all of a sudden you got thrown a curveball and has to play in a different field.
You can see it. So we do the percentage for this. And then we get 13, and 13 in hex is D. I think. And then we do the same number divided by 60. And then we get 2989, and then we do the percentage. which is this number times 16 pretty much.
Oh, wow. Your word is going to end in
think it's
die
Wait,
in leet speak anyway, right?
Right. Am
I think
I-
your word in leet speak ends in die. Because you got DIE, right? The last three letters.
No, isn't it BADD?
Oh, you do? I
It's
thought you got a
baddie.
one before.
Baddie, that's what it means.
Oh, is it?
Uh,
I thought you got a one for the previous remainder. You got a three for the last remainder, and then you got one for the remainder before that. No.
I am going to share my screen on the previous
Okay,
one.
okay.
I did it
you got
before.
remainder
so
3, remainder 1, then remainder 13.
I shared the right screen. Good thing is I already did it before, so here it is.
Oh, there it is. Okay, you got three. Oh yeah, DI. Oh, DIE. Okay, so I only saw the DIE. So I saw your word ends in your thing ends in die, but it's baddie. BADDIE. That
read
is
it-
cool. That is cool. Thank you.
So that was my original process, and thanks for getting me on a tangent after a tangent after a tangent. But if you can, Susanna, please, I guess use the way that you're trying to show me. I guess if you can clarify it a bit more, that'd be appreciated.
You're muted, Susanna.
Yeah,
Okay,
I think that would be great.
So the way I do it to find it is I just first use the slash sign to
Mhm.
get the first part, and then I get the remainder for the
Yes.
next part using modulus, and then I keep on dividing and then using modulus until I can't anymore. So I keep on trying to find the remainder using modulus, and then usually the modulus is what spells out the word.
Hey, do you want to work through an example, Susanna?
Please.
Yeah, is that all right?
Yeah. I was gonna work through a different problem, but
Yeah, sure. Pick your problem, and if you want time to think about a good one, someone else can step in the meanwhile and do
I
that.
have a
If you
couple
want,
problems that I already created, but I could try to create new problems.
I like the ones you shared in the chat. You could look at those.
Yeah, we can look at those.
Hey, I didn't see it. Wait, so it wasn't in the chat window here, not in Reddit.
Yeah, I could just. Should I resend it?
No, I got the chat window here.
Okay.
It's
We
on the
could
iPhone.
try to walk. I could try to help someone walk through that if someone wants
I mean,
to.
I can share screen. But
I can share. Oh, yeah.
sometimes.
Who would like to walk through it?
I'll volunteer as tribute.
Okay.
Uh,
Okay.
Okay.
You could share your screen, and then I could try to explain certain things.
Photos, share. Oh wait, actually, let me. This is gonna be weird, but let me open this in a different thing.
Yeah.
Open
Okay.
like this. Okay,
Uh.
that's the exact same
Yeah.
thing.
Fei actually solved it the way. Made all the calculations
All right.
for the previous. For the problems I created, I wanted to kind of help explain signed versus unsigned binary numbers because that's something I got really confused by. Signed versus unsigned binary numbers is pretty much indicating whether a number is negative or positive. So on the first problem, you could see that usually the farthest left bit indicates whether it's negative or positive. So if it's a 0, it's positive. If it's a 1, it's negative.
That's for a signed bit,
Yeah.
right?
Sign
Yes.
if it's negative or positive. Do you want to give a crack to see what that number is first?
Sure. So
Yeah.
the way I would do this is I would just say, okay, so that's a 1, so that's going to be in the to the power 0 spot. So I'm gonna say that's 1.
Hmm.
Oh wait, that's a huge.
Oh, it looks good. Oh,
Looks
I
good.
see.
Here, let me. So that's 1 plus, and then that's a 0, so nothing there. And then that's 4, so 1 plus 4 plus 0, and then plus another 1, so that's gonna be 16.
Mhm.
Plus another 1, so that's gonna be 32. And nothing, and that's 22. This is how I'm, don't put me in a math class, please. But, so that's gonna be 48, 52, 53.
53 is correct. And then the other ones, do you want to solve them real quick? They're pretty easy.
Yeah, so that's gonna be 3. That's gonna be, is that gonna be in 2's complement form?
Oh, no. So these are regular binary. So
These are
I
all
just
regular
wanted
binary. Okay,
a very basic warm up before the harder one.
yeah. So that's going to be 3 plus 4 is 7. I think, no, wait,
Nope,
yeah.
No.
That's an 8, not a 4.
Remember what I said
1,
about
2, 4, 8.
signed. So it is signed.
So that's -3, right?
-3, correct.
There was
Oh,
a disadvantage with side
Oh,
numbers, I
is
remember.
this in sign magnitude or two's complement?
Yes, these are all in signed.
Yeah.
No, sign
Sign is a lot
magnitude
easier.
notation. Is this a
Signed.
sign magnitude notation or two's complement?
Signed. So
Sign magnitude.
yep.
Okay.
Just to recognize signed versus unsigned real quick.
okay.
So I
Um,
noticed that side numbers are technically 1 bit less, right?
Yeah.
No.
Yes,
Yes.
Because
So
so that means the max number for
I
an 8-bit
guess
side number is
sign
128,
magnitude
right?
works.
I mean, technically 127, right?
Huh,
So signed versus unsigned, for signed, you get a larger range because you have negative and positive. Meanwhile, what unsigned, you get a larger positive range.
it's.
Yeah, that's what I was
So,
talking
oh
Wouldn't
no,
it-
hey,
wouldn't
can
it
I jump in
minus-
for a sec?
Yeah.
Can I jump in
-8
for a sec?
plus-
Can I jump in for a sec here?
Go ahead.
Okay, what was it, Peter or someone said it is that extra bit, okay? For if the number is unsigned, then you get 1 extra bit to represent your number. And when you have signed numbers having both negative and non-negative, okay? So, and the distinction here is we should get into the habit of saying negative and non-negative and not say negative and positive, because if we say negative and positive, then where does 0 go, right? There's no place for 0. So, and again, so that's one of the terminologies that you'll find is very, very common among computer scientists and mathematicians, is signed and negative and non-negative. The other thing also is in when you come to sorting, when you say, people say, oh, ascending order or descending order. And again, there, when you see a list sorted, it's not sorted in descending order. People say it's descending order or ascending order. No, it's usually sorted in non-ascending order or non-descending order, because you may have 2 elements, one after another, that are equal to each other, right? So these 2 elements are not in ascending or descending order. So the only thing you can say about a sorted list that may have duplicates in it is that the list is in non-ascending order or non-descending order. You cannot say that it's in ascending order or descending order, right? Or descending order. Likewise with numbers, you say negative. And then with assigned numbers, you have an equal, not more positives or more negatives, because you have 1 bit, right? 1 bit is the signed bit. So you have negative numbers and you have an equal number of non-negative numbers. So, you have 128 negative numbers and 128 non-negative numbers, of which one of them is a 0. So you have 127 positive numbers and a 0, and then 128 negative numbers. Does that make sense? That's why each bit gives you double the number of bit patterns as you had before, right? So if you had only 5 bits, you can have 32 bit patterns. You add 1 more bit, you have 64 bit patterns, right? In 6 bits, you get 64. How do you get this? 1 bit can tell you if I'm 1, then you have 32 positive negative numbers. If I'm 0, well, if I'm 1, you have 32 negative numbers. If I'm 0, then you have 32 non-negative numbers. So each time you double 1 bit, it will basically double your space. That's why it's exponential, right? Using place value notation, the power of place value is basically the space will be multiplied, the double or triple, whatever the base is, right? The space grows exponentially. The number of possible candidates you have grows exponentially with each extra place you have. So one extra bit means you have double the number of spaces, and half of those can be positive and half can be negative. Does that make sense? I'm sorry to take your time away, Susanna, but I thought it was a useful thing that was also relevant to what you guys were
So
talking about.
someone that's relevant to this. So I noticed that today we seem to be using 32-bit numbers, right? That's the most common kind of number, right?
That's the one Mike.
Yeah, I noticed that. Yeah, on most architectures, when you ask for an integer, you get 4-byte integers now. If you want a 16-bit number, you actually have to explicitly say, I want a short integer.
This.
Yeah, int 8
Very
is one
interesting.
That's
byte.
how you do it in C++ at least. Every language has its own way of doing it, but
So I
Yeah.
think back in the old days when memory was limited, we'd usually use 8-bit numbers, right? Because they take up less memory than 32-bit.
less
Yeah.
bits equals less memory. Yeah,
Even now they do. Even now they take up less memory, right? 8-bit numbers.
Yeah.
always.
Like 32-bit doesn't take up too much memory, so we just use that, right? Even if we
Yes.
aren't using all 32 bits and going over 256, right?
Yeah, that should be the consideration always, is to know the maximum value you need to represent, and then choose your data type based on. So if you're only representing temperatures, for example, right? If you are representing temperatures that are going to be less than 256, then you're better off, well, for 0 to 256, unsigned, better off using an unsigned character, right? It's a char, a character data type, which is only 1 byte. So if you use an unsigned character, you can represent values from 0 to 2 to the 8, the 0 to 255, including.
So I think it's better, but I think that's why I use 1's complement and 2's complement, right? So you won't have to worry about that.
No,
Um,
but in a
So
way,
you can store a negative number without having to do signed sort of thing.
well,
No,
it
no.
does the exact same thing. So 2's complement, that's why I was a little confused, is 2's complement is a signed binary number. It's when you do 2's complement, you're declaring whether or not it has a positive or a negative.
Yeah.
And so it's the same thing, and that's why I got a little confused here, because I'm not gonna lie, I've never dealt with doing just only sign versus unsigned. I've always used 2's complement to declare whether or not I have a negative or not. And
How
so
do you explicitly declare a number to be a 2's complement number? I don't think you can do that in C++.
you can do signed versus unsigned.
Yeah, so you can say
So
signed and
if
unsigned.
I write, if I go back to this, if I say instead say u int 8t,
Mhm.
that's going to make an unsigned integer, and that's going to be in regular form. Funny story, if I take whatever this number is, so that if it's 8 and I store it into a regular integer, so if I say int 8t is equal to, normally this will be a name variable, so let's just name it num, even though it would be on the other side of this, I don't care. Whatever. This is going to be read as if it's in 2's complement, so it's actually going to give me the wrong number sometimes. If this was, for instance, -8, then, and this was a 4-bit, all right? No, 3-bit. Nope, 4-bit, I'm right. 4-bit. I think I'm right. And I'm right.
For 4 bits, yeah, for 4 bits you can go. It says 16 possible bit patterns, right? So for 4 bits you can go from -16 to 0 and then to 15. So it
Alright,
goes
so
from -16 to 15.
it would be 3 then. But regardless, this is going to be 100, right? In binary, the 8,
No,
10.
this is 1, 2, and 4, right? So 2 to the 0, 2 to the 1, 2 to the 2.
So it is a 4-bit then. It does, whatever.
So that's 2 to the 3, and that's 8. Yes, 4 bits.
Alright, so there we go. And then we end up with But if we take this and put it into here, this is going to be read as if it's in 2's complement. So we're actually going to get negative 8.
Is that -8 or -15?
Negative
Oh,
15.
you can
Sorry.
convert it now, right?
You're right.
So here's an interesting problem. So take that number that who's this, Peter?
Yes.
Okay, so this number 1,000,000. Okay, 1,000,000
Yes.
is a 4-bit 2's complement number. Find its value, right? So that's a problem that we can do on screen. Doesn't have to be you, Peter. If anybody else wants to do this and someone else wants to talk them through it, that's fine, or I can talk you through it.
Is
So
it not the
here
negative
is-
max value?
It doesn't matter. You don't know what the value is, but you're just given this number and someone told you it's a number in 2's complement and it's 4 bits long. Okay, 4-bit 2's complement number. You need to find out what the value is.
So I have a question. So maybe you can walk me through this, and I was struggling with 2's complement.
Sure.
2's complement is harder than 1's complement. 1's complement is pretty easy.
Well, 1's complement is the 2's complement is just 1's complement plus 1.
Oh, good to know. Yeah, but
Wait,
I just have trouble doing
I
math
think
with
we're off
binary
topic though. I
numbers.
think we should go back to what Susanna was trying to do. I think we've kind of thrown ourselves into a completely different thing because we're not really dealing with 2's complement here. We're dealing
By
with.
the way, did you guys read module 0? I mean, it's very important to
I
read
did.
module 0. Yeah, because there are examples of this that you may find very helpful. 1's complement is that, by the way, nobody does 2's complement, right? So as humans, we never do 2's complement and 1's complement. These are things that the CPU, the wiring, the hardware will do automatically for you to enable us to store these things. So we don't say, I want this number stored in 2's complement. No, we just say, I want a number. I want a number which can be both positive and negative, right? When you say that, the system will automatically give you a number and internally it'll, take care. You don't know. The fact of the matter is we don't know whether it's being stored in 2's complement or sign magnitude notation or some fancy alien notation, right? So somehow all we know is that we take a number, we put it into the computer, it goes in there somewhere, right? We don't know where it is. We can't even see it, right? Once it's gone, you can't see it. And then you ask for the number back or you add things to it and gives it back to you in a consistent way, right? I gave you a number, I add 2, I get the result, and it is actually the number I gave you plus 2. So it does all the magic in there, but we don't know what notation it is. So what 2's complement, the section on 2's complement in module 0 is intended for is really to give you a sneak peek into what the computer is doing inside in order to handle your negative numbers, right? We don't have to do anything. We just need to know what the computer does with what we give it, and that's 2's complement. Does that make sense?
It does make sense. All right. Well, back to Susanna's problems. The next two, signed and unsigned form. I got just 1 plus 2 plus 4 is 7, and then the same thing, but because this is indicating it's negative, -7. Right. So moving on to the hard one. We have two numbers, A and B. Stored in 1 byte floating notation using the rightmost 3 bits for the exponent. Interesting.
Oh, floating point. Okay.
Can you zoom in a little bit, please?
Oh yeah, sorry,
certainly.
I
Yeah.
made it
Can you zoom
really
in?
small.
At some point, I would also like to see that other problem worked out. Either you or someone else, just to convert the 2's complement 4-bit 2's complement number 1000 and calculate the value. What value is
On
the
the top
number?
left.
1000. What
Oh,
value is the number representing? Right.
Thank you.
Okay, so the question is, two
Oh
numbers
crap.
A and B are stored in 1 byte floating notation using the rightmost 3 bits for the exponent. Both numbers are in 2's complement. If A equals 1100000111 and B equals 00011000, then A plus B in the same notation as A and B are what? So you pretty much want to add A and B, noting that A and B are in 2's complement and they're both signed. Yeah.
Both
So
numbers
we
are in
could.
2 complement. Gotcha.
Both numbers are in two's complement. And something important to remember is that it is in floating notation. And we're using the 3 bits on the right, the 3 most right bits for the exponent in this question.
These ones.
Is that like a float number?
Yep, it's a float number. It's in
So-
floating notation.
So that's how decimals are stored in the computer. They use exponents.
Mm,
Decimals
Yes,
themselves?
yes. That is why it's called floating point. Yeah, because there is a point and it floats into place. So yeah, decimal numbers with fractional quantities are represented like this internally.
we could try to all work through this one together.
Yeah,
because
yeah,
this
totally.
one's a
I'm happy
harder
to
one.
help, but
Yeah.
I'm gonna keep my mouth shut until someone asks me to, or if I feel a need to describe something.
Okay, so what do you think the first step would be?
Well,
Hey,
um,
convert the exponents is the easiest.
Mhm. And technically, I already posted a hint on Reddit. I could just repost it real quick.
why did
Actually, copy and paste. Oh, you can't share it here because we're looking at Peter's screen.
Oh yeah.
Yeah.
We could annotate on his screen then.
Yeah,
Yeah,
we
you
could
can-
just
Yeah.
annotate on his screen real quick.
Yeah. Here.
Yeah, I switched to using annotate because
You
for
can
some
get-
Oh,
reason
I
so
wanna
when,
see
so
the-
when you annotate, anybody can annotate on your screen?
I didn't know
Yeah.
that, but apparently.
Here.
So
Oh,
feel free to
wow.
draw all over it.
I
yeah,
just
can-
annotated.
Well, I can do this. It's not letting me do anything. It's not
Okay.
letting me do anything.
So we could figure out the 3 bits on the side.
Okay, so let's do that
Okay.
first.
So what is A and what is B? Keeping in mind that the A and B are in two's complement and also signed numbers, signed binary numbers.
Yep.
Okay. Anyone want to take a stab at A?
So that's 7 for the power, right?
Not quite.
Um,
For the
the
or
exponent, right?
the
Is that right?
exponent. The exponent,
that
yeah.
right?
Yes.
Yeah, 7 for the exponent. So like then you take a
Is
look
this
at
one 0 for the exponent then?
that binary number there. Yeah, so the binary represent the digit representation of the number, I guess, is going to be like, this is going to expand out to be 1.1000, I think, right? And obviously that's a negative number because this tells you that it's a negative number because it's stored in two's complement. And I think you're supposed to move the exponent 7 times over. Is that right?
Oh, that's a 3. So the 3 most right bits. So it would look like how would I do this?
I thought the 3 most right bit is the power, and
Yeah,
then
it's
the other
the
bits,
power.
and then the other
numbers.
bits are all the numbers, right?
Mhm, yep. And the other
Yeah.
5 bits are the number that you want.
Okay.
So
Yeah.
it'll
So
be blank times 2 to the whatever power.
right.
Yeah.
So it technically should be this times 10 to the 7th power. That's what that
Something
number
like that.
represents.
Yes, but I would
Alright.
double check that one.
Okay, can I chime in?
Yeah.
Okay, so we can do this step by step because I think there are other students who may have been lost. Is
I'm
that
lost.
okay? If we,
Yeah.
I
I'm
can walk
lost
you
in
through.
it's my screen.
Oh, okay.
Okay,
Sorry.
all right. I can walk you through this because I think Susanna is going a little fast for some of the
Sorry.
students. No. It's great. It's great because you're working through this in your mind fast, but some students may not have caught up. And I have experience, right? You don't have the experience of talking
I'm really
to others.
proud of you that you're getting this, but yeah.
Yeah, thank you. Can I walk you through this? Is this Peter?
Yes.
Okay, I can walk you through this and then other people can chime in and correct me if I'm wrong, okay? So remember, I may make mistakes, you got to correct me.
All right.
Okay, so the first thing is, let me just, A, right? Let's take A. and convert that to decimal and write it down in brackets on the right-hand side, so we know what it is, right? So intuitively, we can always keep cross-checking the numbers. So A is you make an annotation somewhere, right? So A is basically going to be that first five digits, that's your base, and then the last three are the exponent. Let's convert both of those numbers into a decimal first, okay? And then the way this is written is really you put the point on the right-hand side of the mantissa. The first five digits is called the mantissa, right? So you write out all the first five digits, 11000, and put the point on the end.
Can you see my annotations, by the way?
I can see your pencil moving around, but I can't see. Yeah, okay, there. You put the point there at the end. Yeah, point. Okay,
There.
that is a point. Now,
point.
the exponent is 111. We're going to convert that and do some funky stuff, but also write down the exponent somewhere, right? On the right-hand side, right? Somewhere, right.
Oh.
Well, yeah.
I
okay.
will refrain from using that mouse. So no.
Yeah, it's fine. All right. So this exponent, after we have calculated it, is going to float that point that you put on the right-hand side into the right place in the mantissa. And then that will give us a resultant number. Okay. So what is the exponent? 111. So can someone convert the 3-bit 2's complement number 111 into a decimal value? How do you do that? Now, when we look at the 3-bit number 111, and we know it's in decimal, it's in 2's complement, we know immediately that it's a negative number because the leftmost bit is 1, right? So in order to find out what the value of that number is, we are going to first negate the number, right? So take the number, negate the number, and then whatever the negative value is, the negative value won't have 0 in the leftmost bit, right? Because it's not negative anymore. So whatever that negative value is, the negative of that is what that original number was. Now, is that small intuitive leap, right? We got to be comfortable with. When you're happy with that, we can proceed to the next step. In order to convert a number from 2's complement to its value, right? This is what we're doing. We know that the number is negative. We cannot tell what the value is by looking at the bit pattern in which the leftmost bit is a 1, right? So in order to find out what the value is, we're going to take that number and then we're going to convert that into its positive equivalent. When it's in positive equivalent, right, it's a positive form, we know what the value is because it's just a straight binary number. Okay, so here's what we're going to do. So take that 111, write it down somewhere on the right side somewhere, some scratch area, right? 111. Okay, now in order to convert that into decimal, we're going to negate it. How do we negate it? Take the 1's complement first. Take the 1's complement of that number. Now add 1 to that number, to the 1's complement. Yeah. Okay. So you get 1.0, right? So you get 1. So that value is 1, isn't it? Yeah. Therefore, 111 should be what?
We took 111,
negated 111 and got 1. So what is 111?
1.
Negative.
Yes. Oh, no. 111 is not 1, right?
Oh.
Is it negative 1?
Yes, negative 1. Yeah.
Negative 1.
Right?
The way
because that's how, if that was negative 1, when you negated it, you would have got 1, which is what you got.
Really?
And you can try it out the other way, right? Negate 1, negate the 001. You should get the other one back, right? Take the 001. Take the 1's complement of 001.
Depends on
what is the 1's complement of 001?
And then you add 1, it's 111.
Yeah, right? So those are counterparts of each other, negative 1 and 1. So you can always cross-check this in your mind, right? So we know that the exponent is actually 1. So that is 2 to the 1, right? So instead of that 0.111, you can say times 2 to the 1.
Okay, so 11000, correct? Times 2
yeah,
to the 1.
11000 times 2 to the 1.
All right.
Okay, now we want to convert 11000, which is a 5-bit.
Wait, should that be 2 to the negative 1?
Yeah, 2 to the negative 1. Thank you.
Sorry.
Robert.
Rob, thank you, Robert. Yeah, thank you, Rob. 2 to the negative 1. Okay, so now we want to convert the 5-bit 2's complement number 11000 into its decimal equivalent. Well, what is the value, right?
Hold on.
Yeah.
Also, the exponent should be right here, right? Should it be right here? Right there.
I don't understand.
Should the exponent for that number be right there?
I'm not sure I understand what you're
Suzanne?
saying.
Wait, no, they're doing it correctly. The exponent is
Oh.
like that.
Okay.
Yep,
Okay.
yep.
So it should be, there's no exponent.
No,
That
there
Should
is
is
an
be
the
exponent.
one.
It's negative
If
one.
it
There is
helps
an
you,
negative
exponent,
one is
right?
the
It should be,
exponent,
it should be
yeah.
right here, right? Should the exponent be right there? Or should
an
it be?
exponent?
No.
I'm sorry,
Exponent.
the period,
No,
Period.
the period is the
decimal
most right
point.
3, yeah. But I'm using that as an exponent, the 3 most right bits as an exponent in floating notation.
Okay. And where's the decimal point should be? Where
It's
should
on the
be
right side
decimal
of
point be?
the mantissa.
So
Always
it's gonna
put
be,
the,
it's
yeah,
right here is where it is. I got rid of it, but
Okay.
so if you notice, here's how it was before, and then here's how it was after. The decimal didn't move, but now it's kind of irrelevant because it's on the far right side. Oop, I didn't mean to delete all that though.
I have a question. Where do you get the
Mhm.
2 to the -1 power with 3 things?
So the way that we did that is we took, so this is our exponent, right? This
Yeah.
thing. So
And
I took that, threw it
the whole
over
thing
here.
is still in binary form, right?
It is in 2's complement form right now.
That's what I meant.
So we're going to turn it into regular binary form. So we're going to the inverse of how we get 2's complement, which is we take the, well, I guess we undo the 1's complement. So we're going to get 0, 0, 0. And then the way it made sense to me was that I subtract 1, because when you find 2's complement, you add 1. So subtracting 1 gives you 0, 0, 1. Technically it's negative 0, 0, 1, which gives you negative 1.
Hey, Peter,
Yes.
what you say is correct, but I think, I suspect that it is the harder way for many people to understand
All right.
what's going on. It would be easier, I think, if we just think of the two numbers as negations of each other. One is a negative of the other, and you can apply exactly, you don't have to apply the reverse of 2's complement, right? Because that's really complicated. Because 2's complement itself is challenging for many beginners, right? And then if we tell them, oh, now you got to apply the reverse of that really complicated procedure, they're going to say, no more C++ for me, right?
Gotcha.
So the reverse of 2's complement is also 2's complement. So you don't have to discover the reverse of 2's complement. Anytime you apply 2's complement, it basically inverts itself. Because it's like negative, right? So negative of negative 1 is positive 1. Negative of negative 1 is negative 1. So you can keep on negating, it'll keep flipping.
Would
So
it
you
be
don't have
fair
to,
to view this as like an absolute value?
are you talking to me?
Or whoever. I'm just curious, would it be fair to view this as like you have on the left-hand side, finding whether it's signed or unsigned, and then the rest of the information tells you the absolute value, like the distance from 0 of the number?
Well,
Am
basically,
I
once we
getting this
find
right or
the,
no?
Yeah, I think, yeah, does that work all the time? Because I think the distance from 0 may not work on the other side, on the negative side. This is something certainly worth thinking about. I'm not able to confirm what you said just now, Elizabeth, but yeah, I suppose if it helps to think about it like that, you can. But you can actually very quickly, you will get into the hang of just, it's a number, that's a sign bit, and the rest of it is basically the mantissa and exponent, right? That's all we need. In fact, if you take the negative 1 and positive 1 and 2's complement and add them together, you will actually get 0. Try it out right now. What is negative 1? 1, 1, 1, right? Write down 1, 1, 1. And then underneath that, write positive 1, which is 0, 0, 1, and add them together. Right now, just do it on screen.
isn't that technically an overflow?
Yeah, but you only have 3 bits.
That's what I mean. So if you had a
Yeah, exactly.
That's
And
what changes
2's
the sign
complement,
then, right?
yeah, and it's critical. It's very important that we do get an overflow, right? 2's complement does not make any sense for Turing machines, for example, where you have, unlimited number of bits at your disposal, right? 2's complement is a clever technique where we take a limitation, which is a fixed number of bit size, fixed number of bits to represent your number. It's a limitation, it's a handicap, right? We took that handicap and turned it around in order to make it not a liability, but actually an asset. Now, because we have an overflow, we also have a fantastic method to store negative numbers.
and a great way to do addition and subtraction.
Yeah, great way to do addition and subtraction, right? So now, so just do this really quickly on the side. 1, 1, 1, which is negative 1, plus 0, 0, 1, right? And then you'll see actually 0, 0, 1, underneath, just like you're doing regular addition, right? Yeah, right, 0, 0, 1 under the 1, 1, 1. Right, 0, 0, 1 under the 1, 1, 1. Yeah. Now, if you add those two together, add the two together, draw a horizontal line underneath, a horizontal line underneath. And let's do the regular arithmetic algorithm we learned from school. So 1 plus 1 is what? On the rightmost side. 1 plus 1? 0. And then you got to carry. You got to carry. You got to
Oh,
carry.
yes. My bad. Oh, I hate this eraser. Whatever. Right?
Yeah,
And
yeah,
then
yeah. Go
that's going
ahead.
to 0, carry, 0.
Yeah, and then you still get a carry, which does not fit into your register because it's only
Yeah.
3 bits long, and so you discard it. And so you get all zeros, right? So that's how we can leverage, exploit two's complement to say, oh, I got 2-bit patterns, and if you add the 2-bit patterns, you get 0 for finite bit size, right? So, therefore, I can treat one as a negation of the other. Now, it doesn't matter which you treat as negative and which you treat as a positive, but we find that it's easier to treat the one which has the leftmost bit as a signed bit as a negative one.
Gotcha. All right. So getting back to this question, what so we found 111 or sorry 11000 times 2 to the -1. Oop, and I got rid of
And then convert the two and convert the 11000 also into its
Yes.
value now.
it's also in 2's complement, so I need to convert it
Two's
first to.
complement and also signed.
So I'm going to convert that to +1, and I'm going to get, correct me if I'm wrong, but 0, 1, 0, 0, 0, correct?
Is that right?
Mm,
Yeah.
Okay. And so that's going to be 1, 2, 4, 8. That's gonna be 8.
mhm.
So then I'm
So
going.
your number is 8 times 2 to the -1, right?
Yep.
Yes.
Okay. Now you can do the same thing to the other number and then add them in, in your mind in decimal. And then when you do it in, regular 2's complement, you can find out if the number is, if your answer is right also, right?
I
It
think
takes a lot
I
of-
found it.
You did? Okay.
I used a calculator for, it's 4.
All right. Yeah.
8 times 2 to the negative
times
1
2 to the
is
negative
indeed
1.
4.
It's 8 over 2, which is 4. So that's what you should eventually end up with.
So A
This,
equals to 4.
I'm gonna write that here.
Does anyone want to try to convert what B is?
Oh wait. I might as. Wait a minute. Is 2's complement form when it's not negative? 2's complement form when it's not negative is equal
No, it
to
is.
a regular binary. Correct.
If it says it's in 2's complement, it's in 2's complement. It just means it's a regular positive number.
Yes. So that's just going to be equal to 0, 0, 0, 1, 1. So 3 times if everyone gets how I'm doing that, hopefully 2 to the power of 0. Correct?
Yeah.
So that's just going to be 3.
Yes.
Yes.
So B is equal to 3. I'll put it in my little box. And then A plus B in the same notation as A and B is, well, it's 4 plus 3 is equal to 7.
Yeah, but you have to put it back into the notation that A and B were in. So you have to put it back into the floating notation
0
into its complement.
dot 1, 1, 1 plus 0, 0, 0, 1, 1 dot 0, 0, 0. And if you want me to write it like this, that way we can do our 0, 0, 0, 1, 1 dot 0, 0, 0. There, that's a little better. And then I guess I could just prove that. Would I need to convert the top side 2 regular binary before I added these two together?
Yeah, you cannot add 2's complement numbers like this,
Yeah.
right? Because yeah, you got to make sure the exponents are the same before you can add the mantices, right? Because if I say a times 10 squared plus b times 10 cubed, you can't add a and b until you get
Yes.
the, yeah.
Um,
One thing you can do is see if you can convert the first number to have a 0 exponent, right? Because the first
Okay.
number was 4, isn't it?
yes,
So you can convert that to a
the 2's
0 exponent.
complement thing of. The only thing I'm confused by is that if this wasn't, if this is 2's complement. If this was 2's complement, would this not be a negative number?
It is. Well, hang on. Oh yes, of course. It would be a negative number. Yeah. What were we doing? Well, I don't know. There must have been an oversight somewhere. Thank you for pointing that out. Somewhere along the way we just missed it. Yeah. That is a negative number. The mantissa is negative.
Is it -8?
What is it? So when you converted it, you got, well, what did you get when you converted it?
I got 01000.
And that is 8, isn't it?
Yes.
Okay, so this must have been -8.
Okay.
So it's
And
negative
that
8
does make
times
sense actually, because if you look at the original number,
Yeah.
that indicates it's negative. So then we are left with 1000.
Yes. So that is basically 100 times 10 to the 2 to the 0, isn't it? Because that's 4.
So that would be -4.
-4. Oh, it's
Gotcha.
-4. Okay, so it's -4. That means you're -4. Yeah, okay. It is -4. But eventually, when you yeah, go ahead. We'll
Okay,
cross
does
that
everyone
bridge.
understand that, by the way?
What do you not understand? Sorry.
I was asking to make sure that everyone watching still is
Yeah.
following what I'm doing, because I realized I was sort of in my head.
It's
Um,
processing.
Okay.
Let's make
So,
sure everybody understands. Okay,
I
not
think-
just Elizabeth and.
So I think A is
Susan
technically
and Chad.
-4, right?
There's a lot of people who are silent.
Yes, A is -4.
Hey, a lot of people who are silent, not just 4 of you, okay? So let's make sure if anybody is like totally lost, they need to be okay or speak up. Okay, speak up and get clear on these things.
So why did you leave B at 00011?
Because, okay, so in 2's complement form, if I were to convert this back to regular, correct me if I'm wrong, if I were to convert this back to a regular form, I would get exactly the same thing.
Oh, good to know.
Am I correct in that?
Wait, by regular form, you mean standard notation, correct?
Yes, standard.
Okay, just making
I
sure.
know
It's
that
a
2
regular
to the
binary.
zeros. I understand the 2 to the 0 because all that's zeros, you know?
Yeah. But basically because of that, whenever you see that both numbers are in 2's complement form, if it's not a negative, so if this is a 0, not a 1, read it as normal. Just read it as normal, and you will get the right answer.
And it will always be the same when you try and convert it.
I'm pretty sure that's right. Anand, is that correct?
Yes, so here is the
Okay,
tip, right?
just making
If the
sure.
leftmost bit is a 0, then it doesn't matter. You can just interpret that as a straight negative number. It's a straight
Positive.
binary number. Yes, binary number.
So
this-
non-negative.
Yes, straight regular binary non-negative number.
So I think, because A is negative, so it technically is -4 plus 3, and that's -1, right?
Correct.
So that's A is -4 in 2's complement form, right?
Yes.
Does that make sense? I hear a couple of sighs in the background.
No, this makes a lot of sense to me, but it may not.
Yeah, but what about the others? I'm pretty sure I heard some people sighing.
Yeah, I kind of just stayed silent because at first I was a bit confused why one number stayed the same.
Yeah.
Okay.
It's just still processing. I'll get there,
Okay.
I think.
All right. And
This week is okay.
Elizabeth, if
Yeah,
you,
I think
yeah,
this week is okay.
Elizabeth, if you never need help, you can ask. Just ask.
Yeah, Elizabeth, I'm willing to walk over some more problems with you in Discord later if you want.
I can join
Okay,
that.
yeah, that'd be great.
But yeah. So going back to this, do you actually want me to solve this? We know it's gonna be -1, but I can prove that it's gonna be.
No, you can't. So when you have it like this, you can't add those
Oh
two
yeah,
numbers.
no, I would need to convert this. So
Yeah,
then
yeah.
that is equal to. Okay. So you're saying I should convert this exponent to try and get it to normal.
Yeah, maybe. So this is basically -8 times 10 to the -1, right? And then -8 times 2 to the -1.
Yes.
So what you want is something times 2 to the 0.
Yeah.
Yeah.
So I'm confused though how I would do that. I know how to do
Yeah.
that in math, but how would I do that with just binary?
Well, you just convert -4 to 2's complement and you're done, right? So because it's -4 times 2 to the 0, isn't it?
Yes.
So what would -4 in 5-bit 2's
Gotcha.
complement be?
Okay. So my understanding at least of -4 would be I have 0, 1, 0, 0. I'm going to convert that to 2's complement. So I'm going to do 1, 0, 1, 1. Is there a way to indicate that it's going to be negative or?
No, don't
Okay.
worry. Yeah, you're doing all the things here.
And then I'm going to add 1, and I'm going to end up with 1, 1, 0, 0.
Yeah, so that is -4.
Gotcha. Okay, so then I'm going to erase this, and I'm going to end up with, and this is actually a 5-bit signature, so 0, 1. Oh wait, that doesn't work anymore.
Why doesn't it work?
Well, because it would be.
Oh, it's -4. Hang on, something is wrong in your conversion. You took negative. You want to convert -4. You did 4-bit. The
Yes,
Mantis has 5
that's what I
bits,
mean.
right?
That's what I was meaning.
Yeah. Okay.
That's what I meant. So if I add a 0 here, then I'm gonna end up with that. So then I'm gonna end up with that.
Yes.
1, 1, 1, 0, 0, like that. Dot
Um.
0, 0, 0.
Yeah.
and
Okay. Got it.
and so
Now you can add the two mantises together.
then now I can add them together. Okay. So 0 and 1 is going to give me 1. 0 and 1 is going to give me 1. 0 and 1 is going to give me 1. 0 and 1 is going to give me 1. 0 and 1 is going to give me 1. You're right. That does in fact equal -1.
And then the 3 zeros for the exponent. So this is 1, 1, 1, 1, 1 times 2 to the 0, which is effectively 1, 1, 1, 1, 1, which is a -2's complement number. Now convert that. Yeah, convert that to a positive number, or convert that to find the value. Yeah, it is -1, right?
Yeah.
Because if you take the 1's complement of that, you get all zeros. Add 1, you get 1. Yeah.
Yes. Indeed.
So there you go. So you got the answer, doing it both ways. You did it in math in your head, in the decimal world. We did it in decimal world. We got -1, and now you did it in 2's complement also. It takes a little while. It takes a little while for 2's complement and sign magnitude notation and really what they are, rather than the calculus of 2's complement, which is you do this, you get that. You do this, you get that. That is easy to master. After a while, we say, okay, given any pattern, I can convert that into 2's complement and so on. But understanding the reason for doing that, the motivation for 2's complement, what does it give us? What can we conquer using 2's complement as a tool? What can we build? So that takes a little while, and I don't know. I can't. Nobody can teach that to you. Nobody taught that to me. But
I'm
it is
not
something
gonna lie.
that
I've
you'll
taken
do.
multiple computer science courses. I've had to learn 2's complement about 3 or 4 times now, and it's clearly not still intuitive for me.
It'll take time.
And likewise, because when you're programming, you're not, as you said, we as humans do not deal with 2's complement. like ever.
Yeah, I can tell you, it can be hard at first, but once you get it, it should be easy, right?
Yeah.
And
Yeah.
same goes with, I'll be honest, binary math was pretty hard for me at first, but it gets easier as you do it because we don't really do that sort of stuff, right?
Here's a tip. Whenever you're stuck with any problem in binary, whether it's exponentiation or
You
really
convert it to
complex,
decimal first. If you're
yes,
stuck.
yes, exactly. Right?
That's what I
Just
do.
forget about
But then you convert
yeah.
back after you solve it. Is that what you do next?
Yeah. If the problem requests me to keep it in binary, that's honestly what I do. I convert it to decimal first thing I do, math it out, and then convert it back to binary.
Oh no, that's not what I meant.
But to do that for a computer though would be a lot of overhead, and it would waste the
A
efficiency
computer
that
does
we're
not do
talking
that
about.
at all.
So it is good for like intuitively learning it, but to also know the I guess the arithmetic that goes into how the computer itself adds up these states of ones and zeros, shows us why why computers are so fast at like computing large numbers.
Exactly. So I think yeah, we don't. It's just a means of understanding what goes on in the background.
Yes.
We don't convert for this problem. I didn't mean convert that to decimal and work it in decimal and then convert it back to twos column. That's not what I meant. No, I mean to understand the concept. Anytime any concept is unclear in binary, not twos complement, in binary, forget about the problem completely. Completely forget about the problem. Pick a similar problem in decimal. Like, if I say, how do I add pi and 47 times 10 to the 5? You were talking about decimal here. What is 47 times 10 to the 5 plus 3.141? How do I add those two? Now, you know how to do that, right? You've been doing that since you're, since middle school, maybe, right? Adding two decimal numbers, you know how to do it. So, but we do that mindlessly, right? When we have to add two decimal numbers, we just do that mindlessly because we know how to do that. The trick here is to not do it mindlessly, but when you do the decimal algorithm, because it's an algorithm, when you add numbers in decimal, you carry and borrow, all of that is part of an algorithm. We don't know, right? We know, now we know, but when you first started. So, but think through the algorithm in decimal and say, no, what do I do? Oh, I actually borrow one from here, which means I take the 10 and turn that into a 9 and take that one away to the right-hand side,
Yes.
right? Same thing happens in binary too. So, and then in the module 0, I gave you an example of how 2's complement also has an exact analog in 10. In base 10. Suppose in base 10, you didn't have the negative sign, right? Suppose English and the numerals didn't have the dash, and you still had to represent negative numbers. How would you do that in decimal, right? So in decimal, you can have the equivalent of 2's complement in decimal, which will be 10's complement, right? And in the modules, I show you how you can represent negative numbers in base 10 using 10's complement. And it's so once you understand how 10's complement works, you would say, no, I don't care about the base. It could be 10, 15, 27, it could be 2. I don't care. The same technique is going to work everywhere, anywhere in the universe, right? Different planet, the same technique will work. So that's what I meant by saying anytime we are, confused by something that happens in binary, forget about binary. Imagine that you're now in decimal world, see how you'll do it in decimal, and then the same technique, not the same numbers, the same technique will also work in binary. Does that make sense?
Yes.
Great. Okay, now thank you so much for this demo, Peter.
Yes.
Now I think Susanna said she was going to work
Susanna
with some...
Susanna sent it in chat. I'm just the one who screwed up all the math.
No, it's a fantastic, and I think I in the process of working through this, you also brought up some of the other nuances, right? Because if you just work through it, there's no use. But what you did was work through it and also brought up potential bottlenecks, potential hurdles where you can get stuck, and also some nuances about numbers and the underlying. So that's the important part, right? Because everything else we can get, but this we can't get until someone actually watches this video and watches you working through this thing. That's fantastic. Thank you so much, right? And Susanna, she said she was going to walk Alisabeth through some examples. Well, ideally, everybody should benefit from that, not just Alisabeth. So I would request, Susanna, if you're able to, you and Alisabeth, right? And I know Alisabeth does not want to have, a camera posted on the video posted on YouTube. So maybe Alisabeth could just have a screen. But if you can record that session and post and share it on share it on a YouTube channel. I'll share it on a non-linear media channel. I'll just make it make you a there's a whole bunch of students from my past quarters who are
that's no problem.
Yeah, okay. Thank you. Yeah, anybody else who wants to take a turn and do another number or convert? You can convert a number from two's complement or binary or take it. Take this screen. Maybe someone wants to do their name, right? Base 27. Right? How about floating point representation in base 27? How's that? That's really cool, isn't it? All right. So suppose I tell you what's the factorial of take a big number. Well, let's say 10 factorial. Right? What is 10 factorial in base 27? Floating point representation, right? Represent floating 10 factorial. No, it's going to be a big binary number. No, 10 factorial. It's 300,000. 300,000 is still less than
big number.
No, 300,000 is it's just you can fit it in a long, right? Because 2-byte number is 65K, already goes to 65K. So just need to double it a couple of times.
By which language, if you mind me asking? Correct me if I'm wrong, but a long is different depending on what language.
Long is 4 bytes, I think. Isn't it a 4 or 8? I think a long is 4 bytes.
All right, I'll take your word for it.
No, you should never take. So that's another thing in my class, okay? Because every time I say I give you 10 facts, I'll give you 2 facts that are wrong, okay? So that is meant for a purpose. That is the purpose of that is so that you will never ever in your life take my word for anything. Okay, never take my word for anything, because I might say after this run into 101 and hit a car. Okay, so you shouldn't take my word for it. So yeah, please don't take my word.
Actually, you're right. Long is 4 bytes for 32-bit computer, but most of us, I think we have 64, so it's actually 8. I think.
Oh, is it?
I
I didn't realize that. So on a modern Mac, on a new Mac, I don't have the latest. Oh, actually, that one in the other room, but I didn't realize that long is also 8 bytes now.
Yeah, that's what it says here.
Wow. Okay. All right. Yeah, that's great. But already in 4 bytes, you can go all the way up to 4 billion, right? So 2 to the 32. 2 to the 32 is a big number, 4 billion. So 300,000 is not a big number. So take a number, and represent that in base 20, base 27. You don't have to do it in class, I don't know, right? But you can do that. Take a number, represent base 27, or take your name, right? Maybe take Peter, convert that from base 27 to decimal, and maybe add it to someone else's name, right? Alisabeth, Susanna, or someone else, their name also in base 27, and then add the 2, and then see what you get in base 27. And so lots of fun things you can do.
Yes.
Is there someone else who wants to volunteer? Go ahead. I think we have about 15 minutes left before the end of class today. So if someone else wants to.
But on that question, is it better to actually create it use long as a data type, or is it better to stick with like UINT8 or UINT16 so that you can actually specify how many bits?
Yeah, it's up to you, but I don't use. I know some of my other students, especially last quarter, they use int8 and stuff like that. I just use char.
Funny story. I recently, so there's a Reddit post I already made on the subreddit that is me trying to understand how the computer uses two's complement. But anyways, for that, because what I was doing is essentially I was trying to see what happens when I take a two's complement form or a signed integer and I store it inside a unsigned integer. And I used my int8 because otherwise I ended up with an int32, and that gave me a huge number.
Right.
And so to make things simpler, I wanted 0 to 255, and so or negative 128 to 127 in complements form. And so
but I think that's perfectly fine. I think that may be the way that people actually do it going forward. I'm just an old schooler who uses int and short and long. just because I have a lot of code that uses it already.
Yeah, and normally you don't need to. Again, it's a very scenario based thing. Same thing with using signed versus unsigned. Most of the time, you're probably just going to use int. That's it. Very small niche things are you going to have to specify how many bits you use, and then likewise, whether or not it's signed or unsigned. For instance, if I'm trying to evaluate what the binary behind the computations are.
Right.
Yeah.
And when you get to doing loops, loop counters, like I want to do this 10 times or 15 times, 100 times or so on, then you have a counter, right? So conventionally, in the recent past anyway, right, people use unsigned for the counter, not signed. So instead of saying int, they'd say size underscore t, which is basically just a synonym for unsigned long. And but other than that, you're right. You don't, most of the time, we don't have to worry and concern ourselves with, you know, these, but it helps to know. That's why, you know, we're just doing this in the first couple of weeks. When we start programming next week, we're not going to look back on data representation, but you can be sure that those who don't have a solid backing in data representation may not cut the best programs later. Right. And it's not just to do with optimization, right? And people say, oh, you know, if you know data representation, you can use a char instead of an int and thereby save one byte, right? Because, you know, temperatures are only from 0 to 255 degrees and I don't need 2 bytes for every temperature. And say, oh, because I know data representation, I was able to save 1 byte. No, right? So that is in fact, this is just someone feeling special about doing something, which really is not special at all. So that's not the way to optimize code, right? In fact, you're better off using int in that case because the compiler, you know, compilers have been around for, you know, 50 years now. So compilers have, and the field has been researched and studied ad nauseum. So people have got so incredible features built into compilers that compilers can now tell if a loop counter is unnecessarily too big. So if you use a loop counter that is a long, but a compiler can find out it only goes to 255, it can optimize internally. Say, oh, I'm going to use a char here because the programmer will never know, right? So compilers are intelligent enough these days to make a lot of these basic fundamental hardware level optimizations, right? Even software level basic optimizations, they'll do.
So hardware level, they could be like, oh, it only goes to 255, let's use 8-bit.
Yeah, exactly. So it only goes to 255. I'll use an 8-bit.
So that's why it's probably better use just, that's why made programmers just use int, right? For their any value.
And
that's not decimal and float otherwise.
I mean, yeah, exactly. But
because that's what I always used when I started coding. I always use int for numbers.
Exactly. And what I was trying to say was that we don't need to concern ourselves so much. We don't need to let these worries be overbearing when we're coding, because the compiler will take care of a lot of these things for you.
Is that why the data representation quiz only takes 5% of your grade?
Yes, exactly.
Because it's not really too much to worry about.
Yes. You need to know data representation, but it's not. It is not the end all in CS2A, and that's
you can still be really good even if you don't know much about it, right?
Yeah, there are lots of programmers who don't know data representation. I mean, you won't have them cutting critical code, right?
Yeah,
but there are a lot of people.
Yeah, I've actually been spending quite a bit of time trying to study this using YouTube videos.
It's very useful. It is not time gone waste, and it's absolutely useful and fascinating too. Data representation.
Yeah, I'm very fascinated by this, by what you can tell, right?
Yeah,
especially the binary stuff, right? How we store numbers, right?
Yeah, and in fact, I mean, we had decimal and octal and hexadecimal and then binary. These are just different ways of storing just information, right? At the end of the day, you abstract it all down. It went from base 10, all the way, abstract everything away, and now we're left with only 2 bits, right? Technically, is it possible to represent information using only 1 bit, not 2 bits? Well, that's something for you to think about. But let's say we're just doing 2 bits, right? So it's just information, and then you can look at more interesting and fascinating problems in this whole field is called information theory. right? Information theory. And so, you know, when we go and buy commodities like gold, right? Gold or silver or bullion, you can say, I want 5 grams of this, or, you know, 2 kilos of gold, things like that. But, you know, can you say, I want this much of information? Can you quantify information and say, all right, I'm going to give you this much information. This is how much it is. And can you quantify information? Now, this is such a fascinating field that you'll find that it's actually possible to quantify information, right? So here you go. Here, weight has a unit, right? So if I want to buy some flour, I say 2 pounds, right? Pound is a unit for, right? Or length has meters, or, you know, or imperial system feet, right? So what is the unit for information? Is it kilos or pounds or meters? What is the unit for information? How can I say this is how much information I've given you? I can say I gave you 2 pounds of gold, but how do I say this is how much information I gave you? So is it possible?
I think it is possible with computers, right? You can say something like, I gave you a gigabyte of information.
Right. Okay. Well,
Yes.
you know, exactly. But how do
Because-
you know it's a gigabyte? How do you know it's a gigabyte? Because, you know, I could have.
I know
something-
what I know what it is. Computers calculate it, right?
Mm,
And you know, a certain
you
amount
need
of.
a computer. So in fact, it's,
I'm not
I-
saying you need a computer, but you can actually, you know, if you look at the binary, every sort of thing on and off is 1 bit, right?
Mhm.
So
And in fact,
there's
you're
like a
right.
certain amount of bits in a byte, right?
Yeah, and the
This-
computer could just find out how many are in that to get, you know.
They can just find out how many, you know, it does all the heavy lifting for you, but you can do it yourself technically, right?
Yes.
So,
in fact,
and they're like a certain amount of kilobyte. There's a certain amount of bytes in a kilobyte and so on, certain amount of kilobytes in a megabyte, so certain amount of megabytes in a gigabyte.
we tend to use these terms rather frequently, yes.
Yeah, for computer storage, you know.
in fact, bits is the unit for accepted unit, a common unit for information. So you can actually say 50,000 bits of information, but theoretically, the unit for information is not log, is not bits, it's something called nits, right? Or nats, right? Where the base of the, so you have 2.17, what is E, the value of E, right? The
Yes.
base of the natural log, yeah. So that's the number of bits. It's a fractional number of bits, right? So, and that's the unit for, here's a more intuitive way of thinking about information, right? So information really is the measure of the amount of surprise, right? Information is just the amount of surprise you get when you are told something, right? So for, as an example, if I told you that the sun rose in the east today, did that convey any information to you? Not
I already
useful.
knew that for quite a while.
Yeah, right. So you knew that. So there's no surprise there. So there was no information in what I told you. On the other hand, if I told you this morning the sun rose in the west, you'll be out the door looking right now. Yes, because that has a lot of information for you because it's surprising. So information really is a quantification of the surprise. And how do you quantify a surprise? So you can quantify the surprise by taking, looking at, so you take the log of the probability, the likelihood, right? The probability of something is a measure of the surprise, right? If something is very likely to happen, has no information for me. If something is unlikely to happen, it has a lot of information because I'm very interested. Is it going to happen or not? So if I told you something that is really surprising, I gave you a lot of information. If I told you that one-legged pony is going to win the race, okay, that's a lot of information. You got to pay that guy a lot of money. 90% of the winnings from that race, you got to pay him, right? Because he gave you some information that is very surprising. But on the other hand, if that guy came and told you, that lightning fast filly up there that's going to win the race, and it's won the race every single day, every single race it's won, there's no information, right? You're not going to pay that guy because that's not surprising.
I actually found something interesting about computer storage.
Mm-hmm.
So the binary bits that make up bytes and all that.
Yes, yes.
So it's technically stored physically as well. On like a storage, for example, a hard drive or RAM or a chip or something, right?
Yeah.
Yeah,
absolutely.
That's where it all starts, physical, right?
Yes.
And
it's all.
like a ROM chip, it's actually very interesting and very intrigued by looking this up myself. It's part of, how the data is actually stored on a ROM chip versus a CD or something, a hard drive or something. Very different somehow.
Absolutely.
But
Yeah.
it is workable, and that's how the computer can work with this data, right?
Exactly. And then what we get out of it is that we don't have to care how the information is stored. All we need to care about is, when I ask for it, am I getting the value back, right? And then it may be stored. You may ask me to store a bit pattern, and I might actually write it down on a piece of paper and give it to you next time you ask, right? So it could be stored in a billion different ways.
Yeah,
You're
there are like
absolutely right.
millions of different ways you can store digital data and millions of different ways to interpret it.
Yeah.
Like for a CD, for example, we have different like pits and lands, and that's how it's interpreted. And each
Yeah.
is interpreted as a 1 or 0. With ROM chip, I think I kind of forgot. It's kind of a bit.
Well, the ROM chip is basically a value of the transistor, right? So inside the chip, you have a whole bunch of transistors, and
That's
transistors.
oh wow.
Yeah.
That's what I saw. It was like a bunch of transistors, and when you have RAM, I think with a ROM chip, it's made to be more durable, so it's more like it's not like these things can be
all
changed.
chips are, yeah. I think all chips are made to be really durable these days. So inside of my phone, for example, and I point this out in every quarter, I think, inside this phone, I believe this has, I've forgotten, I believe this has 64 gigabytes of memory, right? This is an old iPhone 6, and has 64 gigabytes of memory, which means that it has 64, a gig is a billion, right? So it has 64 times 8. That's close to half a trillion. It has a half a trillion switches inside of it, and each switch has a transistor, right? And the way we can tell if a particular switch is on or off is to basically tell if the current is flowing through the transistor or not, right? Because the transistor can be in 2 states. It can be shut off, or it's like a gate, right? So there's half a trillion of those switches right here.
That's very cool.
It's very cool, and even cooler is that in the half a trillion switches. Forget about this phone. Take a more recent phone which has a trillion transistors, right? This is a trillion transistors is 128 gig of RAM, right? People have much bigger phones now. 128 gig, the trillion transistors, and the beauty is that I can address a single transistor. I can say, turn on the 437,640,12, for 43rd switch, turn that on, right? And that can happen in a nanosecond or a millisecond. Bam, 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 like that.
And actually, just letting you know, RAM is not the term for storage. That's known as NAND.
Yeah.
I mean, RAM is very temporary, and I think it works a little differently than those gates, right?
Yes.
I think it kind of runs off the same idea, except they don't store power, right?
One of them is more persistent, and the other. This is the NAND. I think the NAND gates. Yeah. So
I don't know why, but I've been researching why NAND is slower than RAM. But that's a real thing. NAND is a lot slower than RAM, right?
Yes, because of the persistence. I don't know the details.
And did you know that if you play a game cartridge, it actually, the old school stuff, actually, the ROM chips are actually, stored in the memory map, just like the RAM.
And so it'll be slower.
So that's actually also the reason why if you remove a game cartridge, it will cause all sorts of weird things.
Right, because it needs the memory.
Because it's a lot, the cartridge also acts a lot like RAM because of its super fast access. They could, I mean, today we don't really do that anymore. We don't put it in memory map, right? We only ask for data when it's needed, right? And load into RAM. Actually,
I'd say that's not 100% true, but it's most of the time it's true. There is something called a swap space on computers, modern computers.
Where it acts like RAM?
Which acts like RAM, but you don't have to worry about that.
But you still agree most of my stuff is true, right? Like, for
absolutely.
example, a CD-based game, it only reads it when it asks to do it.
Yes.
Unlike with a video game cartridge from, like, you probably remember the NES days, right?
Yes, I'm not 100% sure, but I believe you. I think it's very likely. It's very likely.
I think it's actually mapped to memory, just like RAM.
I'm pretty
And
sure.
that's why if you remove it, you know,
Yeah.
I mean, you
You don't
actually,
have-
I think we're cutting into people's time at this point.
cool, that's
Hey,
enough.
thank you so much. Thank you so much for.
That's enough. I'm
for
going to
this
stop
class.
here. You hear
Chad,
that?
I recommend you make a Reddit post. At the very least, you can get participation points off of this. Research
Cool.
as much as you want and post it out so
Maybe
that
I
we
can
can all
put
see it.
some web pages on hardware
Yeah,
architecture
yeah,
if
please
you
do,
want.
please do.
Great idea.
Thank you so much, guys. Are you guys coming back on Thursday? We'll do more of this, okay? We'll do
I will.
more of this. Think of problems and post it in the, post up some problems that you want to do in class, like today. Try it out on a piece of paper before and then post it. And then on Thursday, we'll do more. Next week, we're going to start coding, okay? And once we start coding, I think we'll start picking up speed. So until then, you have a little bit of breathing time and luxury to fool around a little bit like this.
I'll see you
Yeah.
later. Maybe
Well,
I'll just
at
talk
least for
about
this
these
course.
sort of facts and these gaming facts in the rat post for participation.
Thank you so much, guys.
Yes, thank you.
All right. I will
Thank
see you
you.
on Thursday, okay?
Bye-bye.
Professor.
Bye.
Yeah.
Bye.
Bye.
Bye, guys.
Bye. 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 Bye.